Hello and welcome to this video about Python floats for data handling. We are excited to have you here, and in this video you will learn to use Python floats, which are a fundamental tool for any type of computations with computers and a common data type for data values when performing data handling. For example, Python floats are a necessary tool and data type for most types of fundamental data science and machine learning algorithms, methods, or technology, math, statistics, and data handling. We can use Python floats to represent numeric numbers, outcomes of numeric calculus, parameters of models, coordinates, continuous feature variables, and we can approximate fractions. Moving floats around is a common task in data handling, either moving floats between data storage containers or using them in algorithms, methods, and calculations. Let's talk some more about Python floats. Floats are a fundamental data type in Python, and a Python float is defined as a native Python object and abbreviated as a float. Digitally speaking, a float is an abbreviation for the concept of a floating point or a reference to the Python floats constructor function that creates Python floats. A floating point is a way of simulating some fractional numbers or a way to define numeric coordinates. Currently in Python 3, floats are defined by using 1 bit for designating if the float is positive or negative, 52 bits for the mantissa, and 11 bits for the exponent, for a total of 64 bits or one standard 64-bit RAM memory location. This is not a course in floating point math, so we will simply state that this memory allocation, together with a piece of code defining this as a float, combined with a floating point unit or piece of code that can simulate a floating point unit or perform the same task, is sufficient to use Python floating points. In Python 3, a Python float is a native Python object, and the current Python float is implemented using a double definition in the C language. So what are the consequences of a Python float being a C double? The practical implications and consequences of the double C is that the standard Python float has a large but defined range as compared to the Python integer, which has unlimited size. It also means that the Python float is unexpectedly fast because it is often executed with C libraries, and C is a very fast language, but which is very complex to use. And this also means that the Python float's range is huge, but limited between two incredibly large numbers. And if a number is outside of this range, the float constructor may throw or generate errors if used on numbers larger than the numbers within this range. Three other implications are that certain fractional numbers cannot be defined as floating point numbers, but are rounded to the closest creatable floating point number, and that a Python float can store values up to 15 decimals without any loss of precision. And this mentioned loss of precision can in some calculations create mathematical divergences because the product of the calculus is either unintentionally rounded to the closest double precision number, or because a large number of calculations are serially rounded in the same direction, with an increased error in the same direction as a result. But what we can say is that Python floats are highly useful for most data science and machine learning tasks without modification or augmentation. Now we'll talk some about how Python floats are created. So right, how is a Python float created? And Python creates a float by assigning a decimal value to a variable. For example, the variable real num in this example on your screen. In this example, the variable real num is assigned the value of 5.3, and we have made a comment next to the number using a comment sign or hash mark to remind us that we create a float with a decimal number which has a float value. And we can use the print instruction to type the float to our screen, or to, for example, type check the float using the print type real num instruction. So all right, now we'll type some more code examples. So start up your code editors because we are going to type some code. All right, having started our code editors, we will type some Python float code. And we will begin by naming this video Python floats. So we type Python float, and we will create a Python float using or with assignment. So we type real num equals 5.3, and we use the comment sign, the hash mark, and we type real num equals 5.3. A Python float is created through assignment. And we will print real num, and this will become 5.3. So let's run this code. And it type 5.3. And now we will create more floats and combine them together to create new floats through assignment. So we type floating point 2 equals 3.2. And this is a float value. And we will print floating point 2. And this will print 3.2. So let's run this code. And it printed 3.2. And we will try addition. So we type floating point 3 equals floating point 2 plus real num. And we will state that a float value plus a float value is a float value. So we type print floating point 3. And this will become 8.5. So let's run this code. And the machine printed 8.5. And now we will try subtraction. So we type floating point 4 equals real num minus floating point 2. And we'll state that a float value minus a float value is a float value. So we type print floating point 4 and this will be 5.3 minus 3.2 equals 2.1. Or will it? Let's run this code and test. And here we can see that 5.3 minus 3.2 in the floating point world is not 2.1, but 2.099999996. So let's round the result. So we type print round floating point 4 dot 1. And we run this code. And here we can see that we successfully rounded the floating point number to its mathematically correct number. And this issue is caused by the 64-bit floating point's inability to store certain numbers exactly. And in the ancient days, when we were using 8, 16, and 32-bit floats, this was a great cause for many bugs and problems, also in ordinary everyday calculations and computer applications. With the 64-bit floating points, this is a non-issue for 99.99% of all cases. So right, now we'll try multiplication. And here we will show this little divergence. We will create a floating point for b, and it will be equal to floating point 4 rounded to 2.1. So here we will create floating point 5, and it will be floating point 4 times floating point 2. and we will state that a float value multiplied with a float value is a float value. And we will create a floating point 5b, and it will be floating point 4b times floating point 2. And we will print floating point 5, and we will print floating point 5b. So let's run this code. And here we have an intriguing fact. If we cheat and check the mathematically correct number, it is 6.72 without any more decimals. But here we have obtained two answers, which both are approximations of the correct answer. So we can ask ourselves, which one is correct? And we can say that both numbers become the same number when properly rounded according to the rules of mathematics and measurements. And we can say that round is a bit more correct according to these external rules of the mathematical language and the rules of thumb of measurement, which is a different rule set usually used with programming languages, electronics, mathematics, and the measurement of the measurement system itself. So we can say that round floating point 5 is the rules of math and measurements way. But in reality, when you work with code, and in particular code which someone has written, you will find that this will be the most common. So round floating point 5b most often happens in practice. And we can say that combined with floating points, or you could say either floating points in the software or floating points in the hardware, is a contributing cause to space rockets and aircraft crashes. Missiles missing targets, and measurement errors in general. However, for 64-bit floating points or bigger sizes of floating points, these rounding errors are most often negligible. We could say for any ordinary applications. And this statement is not necessarily true for 8, 16, or 32-bit. Floating points. However, as Python uses 64-bit floating points as the least sizable floating point, this issue will only affect Python applications in certain highly unusual ways, which we will show a bit later in this video. So first, we will try division. So we type floating point 6 equals floating point 3 divided by floating point 2. And we will state that a float value divided with a float value is a float value. And we will print floating point 6. So let's run this code. So right, now we'll take a look at these special floating point calculations. So we'll state that floats are used in many calculations, and we will create a trivial badass example of a floating point equation which goes bad. Or you could say to a very bad place. We start by creating some variables. So we will create the variable result, and we will, in this example, initialize it to 1 because we will use multiplication. So we type floats are in this example initialized at 1.0 for use with multiplication. And we will have a result B, which we also will initialize to 1. So we will type for x in range of 1 to 6, result equals result times x times floating point 4. We will have a result B, which is equal to result B times x times floating point 4. We will print x times floating point 4. We will print x times floating point 4b. We will print result A. We will print result B. And we will print result minus result B. So let's run this code and we will take a look at the result. And here we can see that it iterated and the most interesting part of this equation is this final command where we print the difference between these two equations. So here we can see minus 4.4, 16, 15, 14, 13, 12. So what we can see here is that this is a very small number, but this is a bigger number, and this is an even bigger number. And here it grows and grows and grows. And this number that grows is the difference between what we believe is the correct number when we are talking about the rules of math and measurement. And the other number is the number which you are very likely to encounter in practice. Because when people create calculations, they usually use modularization. And every guy that handles a module will use the round function on his return to the calculation. And likely he actually uses exactly the same rules of math and measurement. It is just that they are being applied in a subtly erroneous way, because the guy who makes this module, he has no clue that a large number of other guys will make other modules, and that all of this will be combined into one big algorithm, and that this algorithm will be run millions and billions and trillions of times, or add millions and billions and trillions of data values together, and that these errors may accumulate as a function of the floating point unit's physical properties in the computer, or as a result of the software that uses this floating point unit, or as a function of the code which the programmer has written. So, all right, we will play a little bit with this example. So we will increase the size of the floats through the loop to visualize the differences due to the round function and this setup, because this is an artificial example which I have designed to display this issue. So we will take this code and we will cut and paste it. And we will add another number like this. So let's run this code. And here we can see that the difference is growing. And you can see something interesting here, that it has crossed the 0. And it is growing and growing and growing. And here it has reached a size which is hideous. And as you can see, if this was a measurement application, then you would have a quite sizable error. And this is the type of error that causes aircrafts to crash. And if you have your computer on for several days, for example, you will notice that it feels like your memory has somehow been filled to the brim and your computer is very slow. And this particular bug is a very common cause for these slowness or crashes over time. So what we will do now is that we will increase the size of the floats even more through the loop to show what can happen over time. So we will cut and paste the same code again, and we will add 2 numbers. And running this code will not cause any problems on your computer, because Python is designed to handle this issue. But if you don't have a proper catch effect for this type of error, then a computer could, in practice, crash. So let's run this code. And this is intriguing, because here we have numbers that are so big that they are outside of the range of this 64-bit float. And it has triggered an overflow error, which has been catched by Python, and Python has been coded to replace this overflow error and the floating point with an abbreviation inf for infinity. So Python believes in this case, because it is not coded for handling bigger numbers, that the number is so big that it could be considered to have reached infinity. And an infinity minus an infinity is not a number. So right, we have some conclusions. If the floating point unit or code cannot properly define a number, rounding that improperly defined number will not change this fact when using that rounded approximated number in calculations as rounded to 2.1 will be returned to even when using round and we can say that this happens the next time 2.1 is sent to the floating point definition and circuitry. And we'll state that this is a property of the floating point definition and circuitry. So here you have first a design of the hardware and you have a design of the software. And these are very overlapping with each other. So there are some things which you can code and some things which you can't code because the circuitry is made a particular way. So you have to cope with this by specialized circuitry. Use a 128, 256, or 512-bit floating point. Or you can simulate a floating point in RAM memory. And we should say that the grave danger is when something in the calculation creates a permanent difference between rounded floating points and floating points. And we should say that this is what we created in this artificial example. Or you could say badass example, because here we have violated lots of rules. So, all right, let's take a brief look at casting or converting other Python data types to Python floats. So we type floating point 7 equals float 5. And this code will cast the int 5 to a float 5.0. And it will create a floating point 8 as float three dot three, and this will cast the string 3.3 to a float 3.3. So we will print floating point 7, and we will print the type of floating point 7. We will print floating point 8, and we will print the type of floating point 8. So let's run this code. And here we can see that the int was cast to a float and that the string was cast to a float. So let's try to convert a suitable Python float to a Python tuple with two Python ints. And these Python ints will describe a fractional number. So we will use a Python float and try to convert it to a fractional number where we have two ints representing the fraction. And a Python tuple is a type of Python storage container, which we will study later in this video course. So, all right, let's type floating point 9 equals 0.5. And we will type that 0.5 mathematically is equal to the fractional number 1 divided with 2. And we will create a ratio tuple, which will be floating point 9 as integer ratio. And we will print ratio tuple, and we will print string ratio tuple 0 plus the division sign plus string ratio tuple So let's run this code. And here we can see that we have floating point 9 first as the tuple, the ratio tuple. So here we have the storage container with 2 integers, and here we print this storage container with some graphical edits. So we cast the first integer in the ratio tuple as a string, and also the second, and we add them on each side of this slash or division sign. So here we can see that we successfully converted or casted floats and strings to ints and ints to strings. So right, this has been a fast and detailed first practical hands-on video lecture about Python floats for data handling. And we are confident that you have learned almost everything which is useful when it comes to Python floats and data handling. And as we said, this is not a course in floating point math. So here we have just shown you how to detect or understand this issue with the floating points. So if you ever sees this, you could say, divergence in the calculations, you know what it could be. So you will have a very easy time to detect this issue and find a way to handle this issue, whereas a lot of other persons will try to find the error in other ways. And technically speaking, the human brain and mind is designed and educated in such a way that people will look for calculation errors. So when you have these rounding errors, they will see 2.1 and they will say 2.1 is mathematically correct, and therefore it is not an error. So people who are not aware of this, they can look for this error forever and they will never find it. So you can take professors in engineering, even professors in math, and you can have them look for this bug all day long, and they will never find it. But you might find it. So, all right. In the next video, we will teach you even more. And if you use the same notebook for the next video, please remember to delete the currently used cells or simply keep your current notebook and start a new notebook for the next video. And we look forward to see you in the next video.